In this video, we'll work through an example that utilizes the law of total probability and, in the process, presents an alternative statement of this law. Consider an example. Suppose that a cell phone manufacturer uses two different factories, one in Minnesota and one in Wisconsin. Let A be the event that a phone is made in Minnesota, and B be the event that it has a defect. Further, suppose that 60% of the phones are manufactured in Minnesota. Among the phones made in Minnesota, 5% have defects. That is, the conditional probability of there being a defect given that a phone is made in Minnesota is 0.05. In contrast, among the phones made in Wisconsin, 25% have defects. Thus, we have information about the probability of event A and the conditional probabilities of event B given A and A complement. But what we want to know is this. Overall, across all factories, what's the probability that a phone has a defect? That is, what do these pieces tell us about the total probability of B? We'll take two different approaches to answering this question. First, consider a contingency table that breaks down all possible combinations of factory locations, A and A complement, and defect statuses, B and B complement. We can get two of the unknown numbers in this table directly from our background information. The probability of A, that a phone is made in Minnesota, is 0.6. By the complement rule, then, 40% are not made in Minnesota. This information thus specifies the row totals highlighted here. Next, consider the inside of the table, starting with the probability of A and B. That is, that a phone is made in Minnesota and has a defect. Though we weren't given this information directly, we do have what we need to calculate it. Recall that by rearranging the definition of conditional probability, we can write the probability of A and B as the product of the conditional probability of B given A and the probability of A. And we do have these two pieces of information. 5% of phones made in Minnesota have defects, and 60% of phones are made in Minnesota. Thus, overall, 5% of 60%, or 3% of phones, are made in Minnesota and have defects. We now have all the information we need to fill in the first row. Since, in total, 60% of phones are made in Minnesota, and 3% are made in Minnesota and have defects, the remaining 57% in this row must be made in Minnesota and don't have defects. We can similarly work out the second row. Consider the probability of A complement and B, that is, that a phone is made in Wisconsin, not Minnesota, and it has a defect. We can write this as the product of the conditional probability of B given A complement and the probability of A complement. Plugging in what we know, 25% of phones made in Wisconsin have defects, and 40% of phones are made in Wisconsin. Thus, overall, 25% of 40%, or 10% of phones are made in Wisconsin and have defects. Then, since 40% of phones are made in Wisconsin and 10% are made in Wisconsin and have defects, the remaining 30% in this row must be made in Wisconsin and don't have defects. Finally, we can get our column totals by adding up the rows. Thus, the total probability of B is 0.13. That is, across all phones made in Minnesota and Wisconsin, there's a 13% defect. Now, contingency tables are great, but they don't generalize well to broader analyses. Thus, let's consider how we can get the same result by applying the law of total probability. Remember that the main idea here is that the total probability of event B is the sum of its non-overlapping parts. Thus, here we can write the total probability of B as the sum of the probabilities that B occurs with A and that B occurs with A complement. But again, we weren't given this information about these intersections. But we were given information about the conditional behavior of B with A and A complement. Thus, we can rearrange the definition of conditional probability to make use of this information. Plugging in, the total probability of B is 0.13. That is, across all phones made in Minnesota and Wisconsin, 13% have defects. This solution illustrates a new way to think about the law of total probability. Again, the big idea is this. When we want to know the total probability, P of B, but we only have information about individual non-overlapping pieces of B, we can combine these pieces to get the whole. What we've learned in this example is that these pieces might either be defined by event B's intersections with, or conditional behavior on the partitioning events AI. More specifically, the total probability of B is the sum of the pieces, the probability of B intersect AI, for I from 1 to k, where we can rewrite these intersections as the conditional probabilities of B given AI times the probability of AI. And what we saw in this video is a special case, where we partitioned event B by another event A and its complement.